Hi everyone, and thank you for coming to Stories from the Playbook. I'm Tina and this is Fred, and we are Google Kubernetes Engine Site Reliability Engineers from London. And today we're here to talk to you about how we approach the challenge of managing the fleet of Google Kubernetes Engine hosted masters. So when you run a Kubernetes cluster on GKE, we take care of the master VM, making sure that all of the core control plane components are up and running. We also control the upgrade cycle of the master VM, and we foot the bill for hosting the master on GCP. So in this talk, we're hoping to give you an insight into how we do the alerting and incident management for GKE, as well as give an overview of some recent outages, our most commonly seen tickets, which might be interesting for you as a GKE customer, or some general good practice tips if you're running your own cluster. But before we dive into the GKE part, what is SRE? So Site Reliability Engineering, our main goal is to work with developers and customers, I suppose, to help protect the service level objectives that we offer to GKE customers. So we do this by holding the pager for the product, but also by working on new features and release processes and helping to review design docs, all to make sure that they follow the principle of reliability. And we also work closely not only with dev teams, but also with other SRE teams in Google that GKE is reliant on. And in London, we have the ads, cloud, and mobile, as well as internal traffic and networking teams. And the ultimate aim of all SRE teams is to automate themselves out of a job. So this is much in keeping with the self-healing philosophy behind Kubernetes, that components of the system can detect and heal themselves without manual intervention. And this means we need to iterate on the pages and the tickets that we see to make sure that they don't happen repeatedly. So for GKE, we have two teams, one in Seattle and one in London, providing 24/7 coverage for both GKE and also App Engine flexible environment. So actually our team looks after all of the managed compute products on Google Cloud Platform. And we onboarded GKE as a product around 18 months ago. So to give you an idea of some of the challenges we face in numbers, as I said, we're one team, but we have two shards globally. And we're supporting a cloud product that's growing exponentially, both in terms of the number of users and also the number of cloud locations. And we're backed by an open source project with more than 1,000 contributors. We have a pretty rapid release cycle. It's weekly, and the rollout occurs over 4 days across the different cloud locations. And we're supporting the latest 3 minor Kubernetes versions. So in almost every release, we're doing one of the following things: either making a new minor version available as a preview, early access version, bumping a previous preview version to a generally available version once we've seen enough stability, or promoting a previously generally available version to the default version for all newly created clusters, again, once we have enough confidence, or mass migrating clusters from the oldest version in order to maintain this sliding window of 3 minor versions. So one of the central tenets of site reliability engineering is that the headcount of SREs should not grow linearly with the number of developers or the number of new features. So we're going to try to talk to you about how we approach the challenge of maintaining a 99.5% availability SLO for zonal clusters in light of all of these moving parts.
Okay, so you're here for some stories from the playbook. So it's probably a good idea to make sure we start off on the same page and describe briefly what a playbook actually is. I was hoping the SRE book would give a nice succinct definition of what that is, but it doesn't say much beyond this, which is fairly light on the subject, talking about best practices and reducing your mean time to recovery. So if we look at GKE specifically, we have a playbook entry for every alert defined on the system. So that might be high error rate on an API server or a cluster being unavailable for too long. And that entry documents the signs and symptoms to look for when an alert fires, and also the possible procedures to help mitigate and eventually fix the issue. Playbooks are a great way of sharing information between engineers on a team and also reducing the cognitive load of the on-caller carrying the pager. Quick implementation detail. Our playbooks are hosted in a number of redundant places, so they're easily accessible even if there's a wide outage in Google. If we look briefly at what an idealized playbook entry might look like, in this case to do with etcd, we can see some signs and symptoms down the left-hand side and some procedures to fix them on the right-hand side. We're going to come back to this in more detail, so I'll move on for now. As I mentioned, a core part of an effective playbook entry is the signs and symptoms to look for when an alert fires. And for that, you need some good insights into how your system is performing. In the case of GKE, we care mainly about the health of the GKE system overall, so that's the systems that serve the cluster lifecycle. And we also care about the health of each and every cluster running within the fleet. So we gather metrics for both of those aspects, showing the request rate for the control plane API server, for example, or the load on a particular master instance. These are all shown on dashboards. So again, there's one for each cluster control plane service and per cluster dashboard, so we can see exactly what's going on each individual cluster. And we aggregate those all together to create a fleet-wide view of different clusters, so we can see what's going on between different Kubernetes versions and also across different cloud regions. Finally, we have a set of probers, and these give a critical black box view of the performance of the system as a user would see it. So, for example, in GKE, we have a prober that continually creates and deletes clusters and makes sure that works, and others that make sure metrics are being exported as expected.
So how did we gather the data that affords us this availability, well, this observability into the availability and the state of GKE clusters? So in every cloud location, we run a job outside of Google Cloud Platform called the monitoring server, and this collects metrics, metadata, and logs from each cluster. So our SLO definition of master availability is based on the core component statuses returning healthy for every component. And if availability is down for even a short period of time, the monitoring server will enact an automatic repair by recreating the master VM. And also based on the number of nodes that the cluster is running, we can also automatically resize the master VM so that it can handle higher workloads. If these actions don't work and availability remains down for too long, or if some other metrics reach some undesired status that like under some predefined conditions, such as etcd backups running too old or master VM disks too full, an alert is sent to the on-caller. So depending on the severity of the condition, this can either be a ticket or it can be a page that requires an immediate response. And this might be location-specific, version-specific, or cluster-specific. So each and every cluster has the ability to page us individually. So that's why we care so much about the reliability of the system. And also, besides our monitoring infrastructure, we can also receive tickets from our frontline support team if they're seeing urgent customer issues. So we thought we'd give some examples of the most commonly seen tickets and alerts that we've had over the past year. Some of these have actually been successfully automated away. So to start off, I'm sure we're not the only ones who've been the victims of Golang panics due to nil pointer dereference. So a few months ago, we saw this a few times in the 1.7 controller manager code, which results in the controller manager crashing crash looping. And sometimes it's due to code that was committed in the open source project actually a few versions ago, but it's on a rare execution path. But due to the sheer number of clusters that we manage, it gets triggered by an edge case and wakes up an on-caller with a page. In a couple of cases, our on-call was able to submit a PR to fix the issue, and then we just need to wait for a new Kubernetes patch release in order to migrate the problematic cluster onto it. And I think we're quite lucky in SRE that so many Googlers are open source contributors, so we have an escalation path to find fixes and submit PRs for issues such as this.
This little robot character represents the service accounts which GKE uses to interact with clusters as they're running. And there's one of these in every customer project. It's also possible that a customer can disable these for whatever reason, and this limits the ability of the master instances to manage the cluster, and also the ability of the control plane to interact with the cluster in general. Nowadays, if that happens, we don't get a page. We move the cluster into a specific state and notify the customer that this has happened and that they need to solve the problem if they want to by re-enabling the service accounts.
And then Fluentd, you might be surprised to see that, or may not be surprised to see that on this slide. So we use this to export logs from both the master and the node onto our logging API. And this creates an alert because at some point in time, it was the largest user of CPU. And even though it's not a core component in itself, we definitely don't want it to starve other critical processes on the master. But it's also vital that we have these logs for debugging purposes. So we alert when this add-on is not running properly.
We also see quite a few instances of clusters becoming unavailable due to the workload that is being run on them. Often this is simply due to some load testing where a customer's kicking the tires a little too vigorously on their cluster. Sometimes it's due to a slightly pathological configuration of the workload, for instance, one namespace per pod, or simply too many jobs simultaneously submitted. These conditions can combine together to essentially denial of service the API server and cause other critical core components, such as the scheduler and the controller manager, to start crash looping, and that can result in an unhealthy cluster.
And finally, everyone's favorite distributed key value store, etcd. Let's go back to the Playbook example that Fred showed earlier. So this is obviously not a comprehensive example of a playbook entry for etcd. It's a snapshot of what our playbook looked like when we were experiencing two symptoms repeatedly. And I think it was the most common cause of pages a few months ago. So first of all, MVCC database size exceeded. So this is referring to BoltDB and the multi-version concurrency control feature that's backing etcd. And this is what allows etcd to handle one write transaction and many read transactions concurrently. So what we were seeing was that there was a bug in the version of etcd that we were running, which meant that this database would expand and become increasingly defragmented if you happen to have a reasonably long read transaction during which many writes occur. And the chances of this really increase if your cluster workload is relatively high. So a short-term fix for the on-caller who gets paged was to, of course, check the playbook entry, then log into the container, and then call a manual etcd compact or defrag command, and or resize the machine disk. Longer term, the fix that we actually went for was to actually run an extra component on the master that would just simply periodically call etcd defrag. That proved to be pretty effective. Another symptom that we saw a few times was crash looping etcd. And this was triggered by a bug in the write-ahead log. So what happened was that once etcd crashed, it would replay its write-ahead log, processing all log entries in order. which can include some long-running reads. And this could take much longer than the 15 initial delay seconds setting that we had for the etcd containers liveness probe health check setting. And this meant that kubelet would cause etcd to restart again and therefore result in this crash looping behavior. This was fixed by the on-caller simply removing the initial delay second setting from the health check. And this meant that etcd had an indefinitely long time to restart, but the underlying fix was made in a later version of etcd. And the last section on leader election issues is an example of a preemptive playbook entry. So in December 2017, we launched high availability clusters as a product in GKE in beta. And this is where a cluster is backed by 3 masters across 3 different zones in one region. So previously, all GKE clusters have just one hosted master. So it's only with this high availability clusters product that we're executing the leader election code paths in etcd. So this is an example of some steps that the on-caller can take if they discover leader election issues.
Okay, so here are some other common procedures that we'll use that are somewhat generic, but apply in a few cases. The first is simply to roll back. This is something we can do with the GKE control plane quite simply. If there's a regression introduced with a new release, we simply go back to the old one. It's less easy for Kubernetes specific issues. If we're rolling out a new patch version or a new minor version, we can't really roll that back because we might be taking away features from a customer or reintroducing bugs that were fixed in that new patch release. So often what we'll do is cut a new release internally with the fix, roll that out, and then upstream the patches to the relevant open source repo. Another option we have for cluster-specific alerts is simply to resize the master VM that are used for that cluster to a larger size. And often if the cluster is overloaded and that's causing health issues, the larger size will give it the space to breathe and become healthy again. We also have the ability to tweak how an alert is configured. We use this sparingly, but if we think an alert is misfiring, then we can change the conditions under which it should fire and hopefully reduce the noise that the pager is making that way. For example, recently we had an alert configured such that if a single request that it was monitoring failed, it would fire. And that's clearly not a scalable situation to be in. Finally, we also have the option to simply silence the page. We'll do this very sparingly, but if we've investigated the alert to its full extent and believe we can't fix it, then we'll silence it. We'll use this in the case of the controller manager crash looping, for example, where we knew there was a fix imminent, but there was nothing we could do at the time. So what can you do to make sure your cluster stays happy and any on-caller behind it stays happy as well? First and foremost, it's important that your cluster is provisioned for the workload that it's expected to run. This goes for nodes, but also the masters if you're managing those yourselves. Also, the disks backing the underlying etcd databases need to be well provisioned. If there's any throttling there and the disks become a bottleneck, that can be detrimental to the cluster performance as well. You can use resource limits on your pod definitions to make sure the scheduler can do a good job of not overloading the cluster. And this should be a no-brainer, but frequent etcd backups is definitely a good idea. We do this in the order of minutes on every cluster, and there's an alert that goes off if these become too stale. We also recommend keeping your cluster up to date as much as possible, up to the latest patch version, if not minor version. And GKE can really help here, obviously. Also, if you are using GKE, please make sure your service accounts remain enabled.
So we've talked to you about some of the routine alerts where there is a solution in the playbook, but sometimes a large incident, large impact occurs. and that must be root caused for the first time. So in SRE for incident management, we follow a mantra of coordinate, communication, and control. And we have an established protocol in a crisis. So on-callers are encouraged to pull in other team members for help and assign defined roles. So there should be an incident commander to manage and coordinate efforts, operations lead, and a communications lead. So we have established communications channels to identify the impact and notify customers via the support channels. And there's also escalation paths to other parts of cloud and internal teams, as well as our developers who maintain their own on-call rotation for the different subsystems within GKE and Kubernetes. Then after the incident, it's very important to write a postmortem that we can learn from, and it's key that it's blameless. So an important tenet of SRE culture is that the fault lies with the underlying production systems and not with well-meaning humans. And most importantly, we need to execute on action items to ensure that the outage is not repeated.
So that's the theory of incident management. We're now going to look at 3 different incidents that occurred recently and how we dealt with them. The first one is to do with Docker, which of course runs on every cluster master and every node. This started with the release of a new OS image underlying the nodes, and that started to roll out. And it was noticed that if the Docker daemon restarted on that node, then pods would no longer be scheduled on it, which is obviously not great for the health of the cluster and its workload. So the first thing to do is to try and mitigate the problem. And in this case, it was quite simple. We rolled back to using the previous OS image for new nodes and downgrade any nodes that had been pushed forward. So the problem's mitigated, but we still don't know exactly what happened. And that's when we start looking for a root cause. So we knew it was something to do with the new OS image. So we were able to essentially diff the configurations between the old one and the new one. And that's where we see the Docker live restore flag come into play. So then we're pretty suspicious of the live restore flag. So we roll out a new image with that disabled, and everything seems to be fine again. So what went well here? Well, we were able to spot the issue pretty quickly before the new OS image got rolled out too far. And we were able to downgrade affected nodes to the previous OS image, where possible. Obviously, what went badly? Well, there's a lack of testing here. This should never really have got out into the live world. And in some cases where customers didn't have auto-upgrade enabled, we had to ask them to downgrade specifically. We actually got very lucky here as well because there were no alerts firing at this point. We were notified by one of our node team engineers that this was an issue. And yes, we were able to solve it from their notification.
So this outage was one of our greatest hits, arguably one of the longest and most visible outages for GKE so far. Fingers crossed. So this started off with our create cluster probers for the entire Europe geo firing, as in they were not being able to successfully create clusters. And our logs indicated that this was a real customer issue and not just a problem with our prober projects. So some initial investigation showed that no other Google Cloud Platform services were affected. So it wasn't an issue with the network or quota. It was a GKE isolated incident. Cluster creation was failing when nodes were attempting to register with the master. And after a few more hours of root causing, we finally found that the error message indicated that the certificate signing module was the culprit. So the certificate signer was trying to pull an external image from Docker Hub, or so it appeared, and the image was corrupted. So in the absence of an escalation path to Docker Hub SRE, we first explored the mitigation option of configuring clusters to pull from a different location where images were still healthy. So this required us to rebuild GKE binaries, which is something that takes over an hour. In the middle of doing this, we discovered that the images were actually coming from an internal Google Container Registry mirror. So actually what we needed to do was purge the internal mirror's cached image. So in terms of what went well, we had pretty good metrics that assess the proportion of the impact, and unfortunately it was pretty large. We were able to pull in help from the incident response team, who are an internal team of experienced Google SREs that help provide emergency assistance in the case of a major outage. And we were pretty lucky that once we root caused the problem, the Google Container Registry team had a big button mitigation that meant we were able to easily purge the problematic image. So in terms of what went badly, so GKE has many dependencies, which meant lots of paths to debug. So it actually took quite a long time to find the log entry that suggested it was the certificate signer at fault. This means that our most significant action item was to create a more comprehensive list of our dependencies, although this is still quite long, and create monitoring that shows the steps with success and failure while we're bootstrapping a cluster. And even though we didn't need the binary rebuild process, we found that we needed to create a fast-track emergency rollout workflow. So in case of any future outages, we can roll out a fix in a more speedy fashion.
The final incident we're going to talk about is to do with dnsmasq vulnerabilities. It fits really poorly into this incident format that we came up with, but it's an interesting one to talk about nonetheless. Bit of background to start with. dnsmasq runs as part of the kubedns add-on on every cluster that GKE manages. And we were notified by our internal security team that there were a number of vulnerabilities in dnsmasq. From our point of view, there were no symptoms. That's kind of a given with security vulnerabilities like this. And there was no real mitigation here. We couldn't really roll back to a previous version of dnsmasq, which would be our usual strategy. And we couldn't stop dnsmasq running on all of our clusters, because that would probably make no one happy. So what did we do? We cut GKE-specific Kubernetes release versions with fixes included in them, and rolled those out just before these vulnerabilities were publicly disclosed. We had to do this internally because we couldn't leak the presence of these vulnerabilities before public disclosure, but after we were able to upstream the patches to the relevant repos. Everything here went surprisingly smoothly. We were able to do the rollout and fix the vulnerabilities without leaking the presence of them to the outside world. However, we were in the middle of doing another minor version upgrade, and that meant we did 2 upgrades in the same week, and some customers did notice this change. The method of creating these patch releases is pretty heavyweight as well. We had to do it for every version that we were managing, and it's a pretty slow process just to change the version, essentially, of one container running across our cluster masters. So we're now currently working on making that more easy to change. Of course, we got incredibly lucky here that A, we were able to roll this out with no one noticing and without leaking the presence of it. Also, that it wasn't leaked by someone else, so we had to do an expedited rollout. And primarily that this was discovered by our own internal team, so we weren't rushing to catch up.
So finally, when we're not putting out fires, what are we doing? So right now, we're very focused on making sure that the support model for GKE scales as the product continues to experience exponential growth in usage. One of the ways that we're looking into doing that is implementing a problem fingerprinting tool that will identify a smoking gun from panics and stack traces for reoccurring issues across the fleet. And as discussed earlier, our standard repair procedure is an entire master VM recreate. So while this is very effective, it's a very big hammer. And we want to do this in a smarter way and really pinpoint the individual failing components. And we also want to make the resizing of the master VM a little bit smarter too. We're looking into using the Cloud Recommendations API that comes with Google Cloud Platform that gives suggestions on the CPU and memory usage, rather than using a heuristic that's based on the number of nodes. We're also working on the private clusters product, which launched in beta recently. So the challenge here for SREs is to, again, provide a similar GKE support experience when a customer's cluster is not visible on the public internet. And finally, we're looking into how we can contribute to Cluster API. So this is an open source Kubernetes project, and it's an initiative to introduce some management APIs to enable common cluster lifecycle operations such as install, upgrade, repair, delete for masters and nodes. And I think SRE involvement here would involve us taking some of the things we've learned about machine management and trying to apply that in open source with the view that we can use things like the cluster API and things like our internal tools, such as the monitoring server instead. So if you're interested in any of these, please do come and talk to us after. We'll hang around for a while after the talk, and you can find us at the Google Cloud booth later. And we'd also really be interested to hear about any sharp edges or outages and learning experiences you've experienced, and perhaps how you guys do alerting and monitoring too. So thanks for listening, and if we have time, we can take a couple of questions, or we don't want to keep you from lunch.